Welcome back to this final session of today's tutorial. Just get the mouse working. So in this final session, we're going to be introducing the Clarity Enhancement Challenge. So this is the first of a series of challenges that we've been organising, or we're going to be organising within the Clarity project. We'll be presenting the Enhancement Challenge today in terms of the methods, the materials, the problems we've had to solve in designing it, and what we're trying to accomplish through the design of it. And tomorrow at the workshop, you'll see a more detailed technical presentation of the baseline systems and the entrance and the outcomes to the challenge. So to start out, I'd just like to point to some of our inspiration. So there's been a long tradition of common task evaluations in speech technology. And this dates right back to the 1980s with the DARPA speech recognition challenges. So from the 1980s onwards, speech recognition has been progressing largely through the definition of shared tasks, where there's open data sets and common evaluation, and teams are invited to compete in these challenges. For speech recognition, it's actually in some ways quite straightforward because there's a clear objective. You've got to recognize some speech and you know what the transcript should be, and there's a clear way of scoring it. More relevant to our challenge, perhaps, is something more like the Blizzard speech synthesis challenges, which date back to 2005, where you're actually trying to produce speech synthesis which sounds good. And now you need human evaluation. And for this, they use crowdsourced listener evaluation. Then more recently still, there's been like the Hurricane Speech Intelligibility Enhancement challenges, which have been looking specifically at near-end intelligibility enhancement, again needing kind of human assessment. 2014, the Reverb challenge is looking at speech de-reverberation techniques. Another one I've highlighted here, which is quite relevant for 2021, is Microsoft's Deep Noise Suppression Challenge. And this is looking at noise reduction, but specifically with low latency constraints, so real-time noise suppression. When we were proposing the funding that actually is going to be funding these challenges, I mean, there hasn't to that point been any work on challenges in hearing aid signal processing. But just last year, in fact, there was the CI hackathon, which was looking specifically at cochlear implant processing for both speech and music conditions. So, we're seeing a move now of kind of challenges opening up for techniques in hearing. So what do we mean by a challenge? Just to kind of explain, what it is we're trying to do. Well, a challenge, needs a common task. We're talking about something that has a well-defined evaluation criteria and a well-defined set of rules to constrain the solution space. And part of the issue here is trying to constrain things such that you can get not just the best systems, but trying to answer some scientific questions along the way. Then you obviously need common data sets that people can use. Having a common evaluation test set, which is completely essential, so everyone's evaluated on the same exam. But often desirable to have common training and development data as well, so that people aren't kind of just seeing the best system as the one that has the most training data. So we try to constrain, people to use this common set. Then you need baseline tools. You want maybe a baseline system reflecting the current state of the art. This is kind of desirable because if you're trying to lower the bar for research, you're trying to get people from other communities to join in your challenge. You want to give them some idea of what the current state of the art is. You might want to make that software open source so that people can actually just develop from it directly, or not have to work on the whole system, but work on components of a system using the baseline to fill in the gaps. Then obviously you need some sort of schedule, a launch date, releasing the software, releasing the task, some sort of strict submission deadlines so that you can make sure that everyone's had a kind of fair go at everything. Perhaps a final evaluation test set released just before submission. And then finally, a results event. So tomorrow's workshop is basically the results event for the Clarity Enhancement Challenge. And the results event, hopefully the idea is people come together, they discuss their results, and there's kind of like bringing all these systems together and seeing what works and what doesn't work. Progress can be made, and then you can iterate. So that's what we're talking about. As I go through describing how we designed this challenge, there's a few things to keep in mind. And there's various design goals for these challenges, which are kind of important. And I want to stress these now because we've launched the first enhancement challenge, but what we're looking to do is to kind of build a community around this challenge to define further challenges going forward, so that we have the second, third, fourth enhancement challenge after this one. And these are the things we need to consider. So we want the challenge to be aligned with some real application scenario. It's no good if it's solving a problem that isn't real. But we also want to have something that addresses real research questions. It's no good having something which is a very real application scenario, but doesn't lead to any questions being answered. Accessibility, we need things to be free or low cost to enter. So the data we use needs to be free. The tools we use need to be free. And then we want to provide tools to support entrance in diverse research communities. So particularly for us, you might have people coming from machine learning or from speech who have never used a hearing model before, or hearing loss model. So that's something to think about. Transparency. So here, we want techniques to be reproducible. There's kind of a bit of difficulties here around entrance. People want to reserve anonymity so that they don't be embarrassed by a poor scoring system, perhaps. But at the same time, we want this research to be publishable. We want people to make their systems open to some extent, wherever possible, so that we can kind of progress from challenge to challenge by improving techniques, learning what's been done before. Fairness is a big problem for us, making sure the way we rank things is fair. And we'll be seeing some of this later in the talk, and I've seen some of this again tomorrow. There's a lot of discussions around how to do this. And I'm saying now, this is the first time we've run one of these kind of hearing aid evaluation challenges. And I can't promise we've got everything right in this challenge. So what we're looking for, particularly in this workshop, is feedback so that we can improve upon things in the next round. So making a fair baseline system. If you have a broken baseline system, or this can be unfair to people who trust the baseline system to producing good results. Making sure you've got some way of ranking the systems. Then impact, which is really important for us. The impact on these challenges comes from bridging research communities, trying to bridge divides across research communities, and also bridging divides between academia and industry. So I'm very pleased I can show some stats tomorrow that we've actually got a lot of people at this workshop from all camps. So I think we're achieving this. And finally, sustainability. We've got funding that will help us organize the first 3 rounds of these challenges, but after that, our funding will finish. We want these challenges to then be ongoing through community participation, through sponsorship. So how do we make a sustainable set of challenges going forward? So these are the things underlying in the background here. So having said all that, here's the structure that we came up with in our Clarity enhancement, our Clarity challenge proposal. And we're actually organizing 2 parallel sets of challenges. There's enhancement challenges and prediction challenges. So the enhancement challenges, this is kind of easy to explain. I mean, this is what we're doing here, giving people noisy signals as recorded by hearing aids. And people have been tasked to process them in some ways that makes those signals more intelligible for a given hearing impaired person. But in order to do that, you kind of need some prediction of how well you might want objective measures that can predict how well your signal processing is going to work. You can't really put a human in the loop very easily here. So you need objective measures of the sorts that Jim was talking about in the previous talk. Now, we don't really know exactly what works for hearing and sort of processed signals. So we've got a second round of challenges, which are prediction challenges, where the task is to actually say, well, here's a signal, and here's a particularly impaired person. How intelligible will that signal be? And those prediction challenges will hopefully lead to better objective measures that will then feed into the next round of enhancement challenges. So this is the way the kind of structure is meant to work, and we're going to organize 3 rounds of this over the 5-year period. In the diagram here, it's showing these prediction and enhancement challenges working kind of synchronously. we've actually done something slightly different. We've actually kind of delayed the prediction challenges and we're coming running them in the gaps in between enhancement challenges. For various reasons, that's going to work out to be better for us. So before we started the project, we defined, an idea of what the 3 rounds might look like. So the first round is deliberately simple. We've got simple stationary scenes. We're targeting kind of domestic living room environments where there's a target speaker and there's a competing source that might be speech or it might be some noise source. And crucially here, the source can be different places, but it's always stationary. It's at a fixed position. So this is in some ways very unrealistic, but we kept things simple in the first round to just get things off the ground. We didn't want to kind of intimidate people by making a challenge which is basically unsolvable in the first round. So nice simple scenario in the first round. And then the idea is we go into round 2, we'll start making things more complicated. We'll have scenes with multiple noise sources. We can introduce listener head movements. Round 3 is still kind of up for grabs, but the idea there'll be some sort of fully dynamic scene. So the full spec of that is yet to be defined. And of course, the point here is that, we're not the ones to define it. We're hoping to get input from people taking part in the challenges, input from these workshops to make sure that we can keep these challenges relevant. So the timeline for the first challenge was we launched it back in January. We released all the materials for training and development then. People participating basically had 4 months. We wanted the listening a bit longer, but things got all a bit delayed. So it ended up about 4 months for people to prepare systems. There's a submission deadline end of May. Then since May and now, it's kind of people taking part, probably things have gone rather quiet, but that's because there's an evaluation phase where we've got to put these materials through listening panels, and that's taking time. And now we're here at the Clarity workshop event where we'll be kind of discussing the outcomes. So there's 2 parts to this. There's the construction of the challenge itself, and we're going to be talking about the listening materials and how we're conducting the evaluation through listening tests. And then tomorrow we'll be talking about baseline systems, which includes the kind of baseline system that we built for enhancement, and that is actually kind of on the challenge entries, and also the other entrants that have come from people who've been taking part in the challenge. We'll be overviewing those, showing results, kind of what works and what doesn't work. Then throughout the day tomorrow, there'll be individual talks by teams who took part, who will go into details of their systems and how they worked. So today it's listening materials and listening tests. At this point, we come to the listening materials. I'm going to hand over actually to John Culling, who has been leading the team at Cardiff, who have been kind of responsible for producing the materials for the challenge. So John, if I stop sharing my screen, I think you can take control.
I think I've grabbed it from you. Hopefully no one noticed me taking it. We've recorded 10,000 sentences from the British National Corpus, which is a corpus of mainly written text materials from various different kinds of sources. We wanted to have speech that was reasonably natural. So we wanted to avoid, for instance, the IEEE sentences, which, excellent as they are as materials, can seem somewhat artificial at times. And we screened those words to have those sentences to have 7 to 10 words, so that there was a reasonable consistency in the length. And we did our best to get rid of complicated words by using the Couture and Francis word frequency database to screen out any sentences that contained words that were infrequently used. We had a very low bar for infrequency. Basically, as long as it appeared in the database, then it was okay. I think more than once it was okay. And then in a more manual way, we went through looking at the grammar. This was quite important because if you don't have sentences that are grammatically correct, the participants might correct them when they report them back. And that would introduce things that look like errors when they weren't really listening errors at all. So we made sure that they were all grammatically sensible sentences that people could report well. And due to the pandemic, we weren't able to record these ourselves. We had to get a production company to do it for us. And 40 vocal actors produced the sentences, 250 sentences each, which they recorded at home. The interferers, again, this was a little bit impaired by the pandemic. We weren't able to record any fresh material because we couldn't move around. So everything comes from established databases. The non-speech sounds came in large part from freesound.org. But we also, they happened to do a lot of research on washing machines at Salford. So they had lots of recordings at Salford that, lots of recordings of washing machines that Trevor was able to provide us with. And then for the speech interferers, we used the corpus at openslr.org, and that gave a large quantity of speech material that could be used as interferers. And that wasn't screened in any particular way. It was just used. It didn't really matter what people were talking about. So we then had to place these in an environment that would seem reasonably plausible. And we took a domestic living room as being the example that we were going to pick, notwithstanding the fact that having a washing machine in your living room might be a little bit odd. But it's a domestic environment where there might be noise sources, and there might be speech from the television or from somebody else having another conversation. And we produced impulse responses for a room of this sort, so that they could be convolved with the speech materials. It was fortunate that there are actually publications on the statistics of British living rooms. So we exploited those so that we could get reverberation times that were realistic and dimensions that were sensible. The rooms that we simulated were all done using Raven. They were rectangular rooms, but we tried to introduce some realistic variations in the absorption characteristics of different parts of the room, because rooms are not all uniform. So we actually did this in a fairly detailed way of placing rugs on the floor and putting windows on the wall and things like that. So we have a room that looks something like this, and somewhere in the room there is a target, an interferer, and a listener. So how did we arrange those? So the target source is within plus minus 30 degrees of being in front of the listener. So we assumed that the listener was more or less facing the target source, and at a distance of greater than 1 meter, and at the same height as the listener's head. It has human speech directivity, and it's pointed towards the listener. So we're assuming that the speech is being addressed to the person who's listening. Whereas the interferer, it could be facing in any direction. Well, it's omnidirectional, so we just have the sound going off in every direction. Okay, so we introduced when we mixed the target and interfering speech together following convolution, we introduced a 2-second delay after the start of the interfering sound before the target speech begins. And this was done for several reasons. One reason is that in the real world, target and interfering sources don't begin simultaneously. And so that would be a rather, or at least only by chance. So that would be a rather unrealistic scenario to be simulating. But also for the practical reason that we thought that when participants are listening to the materials, it might be confusing for them if 2 voices start simultaneously. They wouldn't know which one they were supposed to listen to. And there are lots of Different ways you might try to deal with that by having male versus female voices or something like that. But if you have voices of different gender, that gives a particular advantage to segregating them, which might not always be there. So what we did was we had this 2-second interval of interfering sound before the target came on, and people were told that it would be the second voice or something that would hear a couple of seconds into the stimulus before the target would start. It also continued for 1 second after the onset. They weren't quite offset. There weren't any particularly strong reasons for that. The speech and interferer were mixed to achieve a wide range of different signal to noise ratios at the better ear. We included a wide range because in the real world, there will be a lot of different signal to noise ratios. And we wanted it to be the case that there was always, something to be gained by any processing that was done. So we let those things vary a lot. But we did do some pilot testing to see what sort of signal to noise ratios the hearing impaired listeners could tolerate. So basically, so that materials were not going to be extremely difficult for them to listen to. We wanted them to have a good range of positive signal to noise ratios as well as the more challenging ones. Okay. So the actual data sets that we produced were several. We had a training data set, which was distributed to the participants in the challenge. And these training sets would be the hearing aid input signals for the left and right ears. These are for a complete scenario, and you'd have the signals for all 6 microphones. The database of head-related impulse responses that were used was for hearing aids with 6 microphones on, 3 on each side. So we included all of those. They were pre-mixed with the target and interferer signals. And we also provided head-related impulse responses. I've already mentioned the wide range of signal to noise ratios. In addition to this, we had a development set. So the idea here was that people doing machine learning would be able to create their own stimuli. And so the targets, the rooms, the interferers were all provided individually, along with tools for putting them together in the manner that I've just been describing, so that you could generate lots of other examples if you wanted to take a machine learning approach. And finally, we had a separate evaluation set. So here we separated off some of the target sentences, and these were then released for the final production of example results that could be tested on our listeners by the contestants in the challenge. The scene to listener pairings and listening audiogram data were also provided to all the participants in the challenge, and JSON files describing the scene characteristics for training and development data sets. So what do the stimuli actually sound like? We've got some examples here. Did I remember to share? I'm just going to stop sharing and restart. I knew I'd forget to share the sound. So hopefully this is an example target.
After all, I meant what I said.
You could hear the 2-second delay there. And here it is mixed with some noise, with some competing speech, should I say.
Tourists enjoy fresh air in our playgrounds.
After all, I meant what I said.
To TfL Rail at Stratford Station.
And that's at a relatively favorable signal to noise ratio of 5 dB. If we reduce the signal to noise ratio to 2 dB, here is the isolated example.
But when he's on the move, it can be difficult.
And here it is mixed with some interfering speech.
Masked. The mass of the coils of
But
the
when
hangman's
he's
knot
on
can
the
be tightened
move,
beneath
it
the
can be
jaw.
difficult.
She won't take the train from Mickleford's.
And here are some similar examples with noise, but you notice that the signal to noise ratios are somewhat different here because it's the difficulty in noise is different from the difficulty in speech.
She did not return to land again. She did not return to land again.
It was a version of the classic little black dress. It was a version of the classic little black dress.
Now, I'm not sure that the speech one shouldn't have been the ones at the better signal to noise ratios, but yeah, those are the more difficult signal to noise ratios. Okay, so that's the listening materials, and I'll now pass on. I can't remember who's doing the listening tests. Is that Michael?
Back to John.
Back to John.
Yeah, Michael can't make it, so I just show the right screen. Okay, hopefully everyone can see a screen saying listening tests on it. Okay. So yeah, so in the next little segment, we're going to talk about how we evaluate this and how we did the listening tests. And a key part of this is in the Clarity project, one of the things we were wanting to do is actually do listening tests from home rather than inside labs. So using kind of remote listening test software. Strangely enough, I mean, we had this idea before, back in 2019, before the global pandemic. This is always going to be the case. So when the global pandemic happened, we're actually in quite a good position to actually carry on with our plan as usual. So I'll be talking a little bit about how we've managed to do this. So first of all, recruitment. So this is work that was done mostly at Nottingham, and I'm talking here on behalf of Michael Ackroyd, who can't be here today, about how we went about recruiting our panel listeners for the evaluation. So we've done recruitment through National Health Service audiology clinics. So the idea here is that we can advertise and we can recruit listeners. We sent out mail shots, we advertised in the clinics. There's an eligibility check to see whether they fit our eligibility criterion. Then if they give consent, then they're approved and they're selected onto the panel. And we actually decided we needed about a panel of about 45 to 50 listeners in order to actually get enough statistical power to evaluate the systems we're expecting to get in the challenge. So our primary inclusion criteria were people above 18. We're looking at mild to moderate hearing losses. So 25 to 60 dB deficits in the better ear. We're talking about people who are accustomed to using bilateral hearing aids. They've either got symmetric or asymmetric hearing loss. We required English speakers. We didn't want to have confusions with kind of non-native listening. So to keep things simple, we have native English speakers, fluent English speakers as well. As you'll see, one of the things we're doing in the tests is we're actually scoring things by asking people to repeat what they've heard. And for us to be able to score that, we need people to speak fluently and clearly. We didn't want to get kind of confounds with the cognitive problems. So we have a screening through a MOCA score. So asking for people who actually have high MOCA scores. Then people who are also, this is quite crucial, confident in using tablets or tablet software. So as you'll see later, we'll be using a little Chromebook tablet to actually be doing the tests on. So we needed people who are fairly kind of tech savvy, so they can actually do this themselves in their homes. And also, final requirement there is they had to have an internet connection. They can be doing these tests in their homes. Sort of client-server architecture, materials are going to be delivered to them. The responses delivered back, so you need a good internet connection. A few exclusion criteria, nothing very remarkable here. We didn't include any people who've got hearing interventions other than hearing aids. there's a note here about something called a PVP shunt. And I think this is something that can be fitted to people with hydroencephalus, which is like a little valve that can be fitted to people's heads, controlled by a magnet, which doesn't play well with headphones apparently. So you have to make sure these people aren't on your panel. And no hearing loss is greater than 90 dB in more than 2 octave bands. I mean, there's a limitation here that we're delivering signals over headphones, and I mean, there's basically an upper limit to how loud we can make sounds. So we're not going to be able to deal with people with severe hearing losses to get things above the threshold. Also, we're screening out people who had tinnitus or Meniere's disease or hyperacusis. So that was basically how we recruited the panel. We did this successfully eventually. I mean, things were a little bit problematic because I think a lot of the audiology clinics that we would be recruiting from were closed during the pandemic. But we eventually managed to recruit 44 participants, 25 male, 19 male, through a Nottingham clinic. So if we look at the stats for those, for that panel, we have a mean better ear hearing loss of about 40 dB. And you can see the kind of distribution here of hearing loss, so often around kind of 40 dB, but on the extreme case up to kind of 60 dB and down to about 25 dB. So kind of mild to moderate hearing loss. And then I think a better worse difference of about 7 dB. So most people are roughly symmetric, but there's a few in there who are a little bit more unsymmetric. If you look at the audiograms for these listeners, so here we can see the full set of 44 listeners audiograms. You'll see actually quite a big range in there. I mean, there's quite a lot of diversity in the shapes of the hearing loss and in the degree of hearing loss as well. So the audiograms is something that we made available to contestants. So obviously, these systems have to be individualized. People are making enhancements for specific listeners. So in the challenge, people will be given pairings of, here's a signal, process it for a participant with this particular audiogram. So that's how we recruited the panel. And then the next part is about the online tests. Before I start here, I'd like to point people towards this quite recent review article, which is like a really good place to start when looking at how to design remote testing for acoustics. So there's a really nice paper there that I'd like to direct people towards. In our project, we basically got 2 bits of software that we've been using. So the first one, which is called Listen at Home, which is going to be used, it has been used for the evaluation of the enhancement challenge. And this is something that presents the process stimuli to the hearing impaired listeners. They verbally report what they hear, and then this is scored by an automatic speech recognition system. And I'll say a little bit more about that in a minute. And then we've got some software from Nottingham called Note, which allows us to collect questionnaire data and do some psychoacoustic tasks for collecting extra data, which is going to be feeding into this prediction challenge. And I'll speak a little bit about that in a minute as well. So the Listen at Home. So this is basically what the panel participants receive. This runs on a Novo Chromebook tablet. So it's actually a fairly low powered tablet. We have 50, I think, of these tablets bought in the project, and they've been posted out to participants or to the panel, along with a pair of Sennheiser PC8 headphones, which is a headphone and microphone set. So every single participant receives one of these. And one of the key parts of this is that we haven't been able to, because of the pandemic, to bring people into any kind of workshop training environment. So this thing has basically got to be, something that's usable out of the box. So we've really been straining to try and make this thing, and we can send it out to people and they can start using it straight away without any interaction with us and start collecting data from them. When they receive it, they turn it on, they see interface a bit like this, or they see a desktop. There's the They actually haven't got so much software on theirs, but they'll have just this little icon here. They'll click on it and it'll take them straight through to the app they're going to be using. So it's really designed to be super simple. The key question when we design this approach is, can we get consumer headphones that are going to be basically loud enough? Participants aren't using their hearing aids. The idea is they take the hearing aids out. They're listening to signals being processed as though by hearing aids over headphones. We settled on eventually this Sennheiser headset. We've got 44 copies of these. Nottingham team actually measured these all, and we calibrated them all and measured them all over using a B&K artificial ear. And the reference set gave a maximum producible volume of 99 dB. So that's when using a sinusoid at 1 kilohertz. And you'll see amongst our sample, there's actually a little bit of spread. The loudest headsets are producing about 100 dB and the quietest one's 94 dB. On the right there, you can see the frequency response of the headset. So we decided that this is probably just about good enough for us. If people turn everything up to the max, for the mild to moderate hearing losses we're talking about, systems are going to be kind of super threshold. So the idea is that listeners log into the tablet in a quiet room. It's all self-paced. They do kind of 30-minute sessions. The tablet connects to a server. It presents them stimuli they listen to. They are told to listen to what they hear, and I'll show you something about how they do this in a minute. And they speak back the words they hear. This goes back to a server, and then we process this offline after the fact. And we do this over and over again. Each listener does about 600 trials, about 3 hours of listening. And I think in total, we're collecting about 20 to 30,000 responses. So the software was, for Listen at Home, was developed at Sheffield, and myself and a PhD student, Jack Dedman. So I'll acknowledge him there. There's a web address there. If you go to it, you'll get to a login screen. You can't actually use it, but you're using an account. So it's kind of, the listeners got accounts and they can log in. But we're hoping to use this software more widely after this project. When they log in, they go to a nice friendly login screen. They can see how many tests they've got to complete. Very important, there's a kind of built-in tutorial which they're encouraged to read. They read the tutorial, it tells them what to do. I won't go for the whole tutorial, but there's kind of key things here about making sure that people know what they're going to expect. They're told they're going to expect speech and noise tests. They're going to have also speech and speech tests. Another challenge we had was trying to make sure that people actually wear the headphones the right way around. This sounds kind of a little bit trivial, but obviously these are asymmetric hearing losses and people have processed signals in a stereo manner. So there's a proper left side and the right side. If people have got the headphones on backwards, that's going to be completely messed up and completely invalidate the test. Unfortunately, the headsets, and you can see here, have a little sort of swivel headset piece where you can see you put this on the left, but you can swivel it around as such and also wear it on the right hand side. So it doesn't really provide a very strong cue to which way around you're meant to wear these. There's a little L here, but it's really hard to spot. So we're trying to use pictures, and I'll show in a minute, we have a little kind of test as well that we make sure through playing sounds that people have got it on the right way around. So trying to make everyone have the things on the right, and then trying to kind of train them a little bit about how to respond. This is actually quite a challenge about how we score these tests. What we're doing is we're scoring words recognized correctly. So it's not keywords, there's a sentence and they report words they heard. Now, obviously this can kind of get a little bit wrong if people start saying all sorts of things that aren't part of their response. So we don't really want people saying things like, I think I heard the cat sat on the mat, or the cat sat on the mat, or was it hat? They've got to try and stick to exactly the words they heard. So we get some examples of this and we try to train them a little bit about doing this correctly. Also, for a lot of the cases, they'll be hearing just fragments because some of the stuff is really challenging for them. They won't be hearing whole sentences, they'll just be hearing individual words. So if they hear a masked thing like this, it is noise, man, noise, come back. We don't want people saying something about a man coming back. We need people to say just noise, come back. We don't want people really rejecting sentences and just saying pass. We want people to be making their best guess. So we've given them various bits of instruction about how to do the challenge. Another key fact here is we haven't fixed the hearing level for the tablet. We didn't think we could fairly do this. We don't know exactly what level participants are going to present signals to us. We don't want the signals being uncomfortably loud for people when they're listening to 3 hours of signals. So our solution to this was to provide a volume adjustment. So before the beginning of each block, each test, and each test is going to be one condition, one system they're listening to. They hear some samples of that system, and they're able to then adjust the listening level up and down until it sounds comfortable to them. And then they continue the rest of the test at that level. So that's something that's been quite important. We can't fix, so we haven't fixed that level, but we do record it. So we do record the level they've actually set things to. Then the headphone check, again, very important. We do this by playing a signal, which is a stereo signal, which simply says left, right, and they listen to this, and they should hear left in the left ear and right in the right ear. If they don't, they've got an opportunity to put the headphones on the other way around. So again, it's quite important, it'll really mess things up if they've got the headphones on the wrong way around, and we can't be there to make sure they have. Another thing that can go wrong is the microphone not working properly. Unfortunately, a bit of a design flaw in the Lenovo tablet, that the socket you plug the microphone headset into is also the socket you charge things through. So at nighttime, they're unplugging the headphones to charge the tablet. Then they have to remember to plug the headset back into the tablet. We're worried about scenarios where they've actually got the tablet in front of them, they've got the headset on, and they think they're listening to the headset, but actually they're listening to just the speakers of the tablet. So we do a microphone check where they speak some words, they hear back what they've spoken, they can report back where they can hear their own voice and make sure things are working. Then when they get into the tests, it's all quite straightforward. They simply are told if it's a speech and noise test, you'll hear speech and noise. They press next, and it comes up listen while the stimulus is being presented. And then it comes up speak when it's finished. They speak their response. They simply then click the next button, and it goes on to onto the next stimulus. The microphone's actually recording all the time. We were worried about people kind of preempting and speaking too early or speaking too late. So we simply turn the microphone on straight away as soon as they press next, and we record up until they press next again. So everything is recorded. If all goes well, we receive signals that look a lot like this. And what you can see here is there's a period when the stimulus is playing and they're listening, and they're in a quiet room, so this should basically be silence. Then you hear them recording their response over the headset. Then there's typically a pause while they kind of recover until they go and press next to listen to the next one. This part of the signal is actually quite useful to us because what you're seeing here is actually a little bit of leakage from the stimulus being played over the headset, kind of cross-talking into the microphone. Now that should be a very quiet signal. If they're in a noisy room with a lot of background noise or the TV on, you'll be able to see it in the signal. If they haven't got the headset plugged in correctly, you'll be able to see it as well. So you can actually use the complete signal to actually do a little bit of a quality check to make sure that things are working correctly. Once they've recorded, we will transcribe the utterances, and then we score them by comparing to the target utterance text. So we get the text response, the target utterance text, and we do an alignment and scoring. This is simply like you do in automatic speech recognition. You line up the two texts and you count statistics on the words correct. For this transcription process, currently we are actually using speech recognition, which is quite interesting. Later on, we're going to actually retranscribe by hand a lot of the stuff to make sure that we actually minimize the number of transcription errors. So if the target was something like, she did not return to land again, and the response was, he did not return to the land, the alignment process would line the words up like this, then count how many words have been scored correct or repeated correctly, did not return to land. That's 5 correct out of 7, so that's 71% correct. Note, we're not doing kind of the other metric, which is used in speech recognition, which is kind of the word error rate, where you also include incorrectnesses for insertions. We didn't do this because we're very aware that a lot of people actually are adding in extra words when they kind of talk to themselves or say things like, I think I heard. Although we told them not to do that, we didn't want them to be scored incorrectly in that way. So we're sticking to this correctness metric. This score 71, we actually accumulate this over all the utterances for the system. So number of words presented for that system, number of words correct, and get a correctness for that system from that participant. So that's basically how the listening tests, which are currently still running, because we haven't quite finished them yet, but I'll be showing results tomorrow for what we've got so far, are done. The other bit of software we're using is the note software, which has been developed at Nottingham. Again, Michael Ackroyd unfortunately can't be here today, but I'll be presenting this on Nottingham's behalf. And this is the software which has been used for collecting extra perceptual data, which is going to be feeding into the prediction challenge test. So here we want not just audiograms, but other measures. So we've got things like triple digit test performance and questionnaire performance. So we're using Note, which is this platform which has been designed some time ago, I think, at Nottingham, which can run all sorts of online perceptual tests. The kind of core developer here, Pedrick Kitterick, and for the Clarity project, Michael, Esther, Jennifer, and Holly have been kind of programming it to design the tasks that we need. So some of this is just quite straightforward questionnaire material. In fact, if you go to, if you've got a QR scanner, you can scan this QR link and it'll take you to the software and you can see for yourself what it looks like. And we use the software to collect questionnaire data. In fact, if you go to this, I think you can type in a Clarity code like this, Clarity-9XX, and a confirmation code, and you'll be taken through to the questionnaires that we're using, so you can see for yourself kind of the questions that data we're collecting. So some of it is just demographic data, age and gender. So the first important thing is this SSQ 12 questionnaire. So this is a simple questionnaire which is got 12 questions, which is designed to measure people's kind of real life listening experience. So it provides scores which are very kind of indicative of how challenging people find it to listen in noise. So this is a kind of standardized questionnaire. 12 simple questions, doesn't take long to answer. And we're also using another test questionnaire called the Glasgow Hearing Aid Benefit questionnaire, which again is a simple questionnaire. It's asked people about their experiences of using hearing aids. And finally, we're using this to measure triple digit tests. So triple digit tests are simply 3-digit sequences in noise. This is an adaptive test. So what they do is they hear 3 digits, they repeat them, or here they actually repeat them, they kind of key them in by touching on the tablet. If they get the correct response, the noise level increases. If they keep getting correct responses, it gets harder and harder. So it's adaptive. If they get an incorrect response, it gets quieter again. So in this kind of adaptive way, we end up estimating a kind of speech reception threshold. So after 40 trials, we can measure kind of the level at which they're getting a certain number of digits correct. And I think this digit triple test is kind of obviously, supplementing audiograms is going to be very important for predicting how challenging people find it to listen to speech and noise. And will be a key kind of input to the prediction challenge that will be running after this enhancement challenge. So I haven't really gone to conclusions. That's kind of where we'll end here. So I've kind of just described listening materials. We've described how we've recruited the panel. We described the way we're conducting the listening tests, how we're doing the evaluation. Tomorrow we'll see more about the baseline systems and the systems that have been submitted and the scores they've got. One thing I haven't discussed here or discuss again tomorrow is actually 2 parts to the enhancement challenge. One was a subjective test using the listening panel, but also we have this objective test where we've given people an objective measure, something called MB-STOI, and they've been asked to try and process the signals to maximize the subjective measure. So tomorrow we'll be talking more about that, the baseline systems, and the results. So yeah, thank you for listening. I think that's my last slide, and that's where I'll finish.